coffee, so we'll have the next talk for today by Hemanta Maji, and he'll tell us about the geometry of secure computation. Yeah. Okay.
You have to.
Okay. So sorry if you. So hope you enjoyed your coffee. We're going to have the next talk of the session today. And it's by Hemanta Maji, and he's going to tell us about geometry of secure computation.
So everyone can hear me? Okay. So thank you for having me here, and thank you all for being here. So today I will be talking about a connection that we have established between geometry and secure computation. I will talk about lamination hulls. These are generalizations of convex hulls and independently motivated by hydrodynamics and partial differential equation literature. And special kinds of these lamination hulls have the ability to model the mathematics of interaction between agents. And understanding the geometry of lamination hull has been an open problem in geometry and algebra. And in our recent work, we resolved this problem about those lamination hulls which are relevant to crypto. And through that lens, if you view, what we have achieved is that we have resolved long-standing crypto complexity problems, which have been open since secure computation was envisioned. And I will tell you a little bit about lamination hulls, the mathematics that we had to invent to understand their geometry. And we will be jumping across a lot of topics in science, very distant subjects. I will try to go slow so that we do not get any whiplash, okay? So the research motivation comes from investigating this problem from secure two-party computation in the information-theoretic setting, where parties in the plain information-theoretic setting. We have two parties, Alice and Bob, and they have private inputs X and Y, and we want to determine just by communicating with each other whether they can compute a function f of xy. Okay, our questions will be of the following form. Can we accomplish this secure computation task? If yes, we want to find the optimal protocol, optimal vis-a-vis, let's say, its communication or round complexity. If no, what is the obstruction to security? These questions have been open since the 1980s. Even their decidability was unknown. Okay, so forget about optimization. So the technical bottleneck here is that the appropriate mathematics to model and reason about them was not known, which we developed in our work. And I will tell you how we systematize and search over this search space of all interactive protocols. If you are more interested about understanding the mathematics of this, there is a summer school where I will be talking about this mathematics soon, in October. So here's the question concretely. We have Alice and Bob. Alice has private input X, Bob has private input Y, and they can communicate to each other. And they want to compute an output Z, sampled according to a distribution that depends on both X and Y. We want Alice and Bob to both agree on the output. We will consider adversaries that are honest but curious. And the question that we are interested in is there a B-bit secure protocol for the function f? More generally, is there a secure protocol for the function f? And for specific to functions where the output is determined entirely by the input of the parties, that is deterministic functions, Chor, Kushilevitz, and Beaver in 1989 characterized all such functions. No such characterization was known for randomized functions with randomized output. Even the fact that these problems were decidable was unknown. So in a sequence of work with my collaborator in mathematics department, Sogato Basu, and my students Hamid Reza and Hai, we resolved these things. And we built some very fancy mathematics that I would like to present to you guys. So at a very high level, this is our geometry of interaction framework. You start by specifying a problem that you want to analyze in security and information complexity. We tell you a way to translate this problem into a constrained optimization problem. Before our work, even a finite representation of this optimization problem was unknown. Then we show that to solve this constrained optimization problem, we can translate it into investigations, a geometric investigation that tries to understand geometries of something called lamination hulls. These are generalizations of convex hull which enforce convexity based on a precondition. We develop a new theory of lamination hulls using by building new mathematics. After this, we can build algorithmic tools describing the sets algebraically, succinctly, and answering membership queries. Given these algorithmic tools, we can go back into our security and information and complexity world, and we can start building optimal protocols for tasks. We can have computer-assisted secure protocol designed. We are not limited by human intuition and imagination anymore, and we can actually identify bottlenecks to security. Okay, to illustrate this entire pipeline, I will give a few examples moving forward. So the impact has not been just limited to cryptography. The theory that we develop extends to mechanism designs as well. And the mathematics that we develop has even broader applications. It resolves open problems in geometry and partial differential equations, and has applications to optimization, complexity theory, formal languages, and computer graphics as well. Okay. So here is our research team. In this talk, I will cover results in these 3 works. As is obvious, our next result will be announced at TCC 2028. Okay? Okay. So let me give a very high-level introduction on what lamination hulls are and what can they do for us.
Can you
Yes.
say something about the definition of security?
Security. It's UC standard UC security. Given the output, you should be able to sample your input. Yeah. But honest but curious adversaries.
Information-theoretic.
Yes, plain model.
And one more question.
Yes.
So when you move to this geometric notion, do you lose something, or is this like without loss of generality?
No,
This is an if and only if you're first.
It's if and only if.
Okay.
So this is another one of the features of our reduction, that the connection that we have established is really deep and accurate. There is no loss. If there is a protocol, we will find it. If there is none, I will give you an obstruction to that security. Yes?
Perfect.
Oh, this is a very good question. It's perfect security. Statistical, I think, is doable. We used perfect security as a motivation and to build a test bed to establish this entire pipeline. But definitely, that's a way forward to go to model that.
And if you consider also expected protocol that terminate in finite expected time, or only protocol that
Yes, we can
finite time?
we can now deal with even infinite protocols. Yeah. So before I introduce lamination hull, let me introduce convex hull into using a new technique. So we have our initial set of points S0, and we are allowed the following geometric action. You can pick 2 points PQ in your old set and join the line segment joining those 2 points in the new set. Note that I did not insist P and Q to be distinct. They can be same. So what it means is that if you choose PQ to be identical, you can actually copy the old set into the new set. So the red lines here show the new points that appear in the new set for the first time. Okay? Is this color coding clear? So here we have joined all pairs, and we have these lines are denote the points that appeared for the first time. If we apply this geometric operation on this set, we get a new set where everything is now filled up. Okay? After this, there is no new point that is added, and this evolution stabilizes. So our objective is to investigate evolutions of sets of this form. It is known that for convex hull, this evolution stops. This is a consequence of a very powerful theorem by Kara-Theodori that says that if you have points in d dimensions, then the interior of a convex hull can be expressed as a convex linear combination of at most d plus 1 points in the original set. Okay, so now let me move to lamination hull, and I will explain how lamination hull differs from these kind of definitions.
Sorry, one question.
Yes.
And is this theorem known for other metrics, or is it only for Euclidean space?
So you can actually work with arbitrary such operators, convexity operators, and there are notions that generalizes Carathéodory number by giving Helly numbers and Carathéodory numbers, after which it stabilizes. There are such generalizations. So yeah, this is a beast in itself that was started in the early 1900s, sorry. A bad habit of saying 90s. I sometimes forget between the age difference of the fields. So let me introduce lamination hull with an example. We have the same initial set, but now there is a precondition. If the 2 points that you have chosen, P and Q, you can join the line segment joining them if and only if their first or the second coordinates are identical. That is, the 2 points are axis aligned. Only then. If they are, none of their first or second coordinates are equal, then you cannot join them by line. Simple rule. Okay, so again, we can take PQ equal to same, and that helps us copy the old set into the new set. And now you can be convinced that this is the only line that could have been joined. Everything else, the line is not axis aligned. Okay? Are we good? Okay. Next, only this line can be joined. Then this line. Then this entire rectangle inside. After that, what happens? Yes, because I ran out of space. Otherwise, I would have kept one more. So a natural question is, under this geometric action, do we have succinct descriptions of these iterated sets? Does this evolution stop? And can we compute the hull, which is the union of all the sets defined in this manner? Is this clear? So these are the research questions in geometry.
And it's always orthonormal basis, right? These holes are always...
This is one example, which is good enough for crypto. But there is a more general formulation. I will come to that. Yes, there was a question here. Someone asked a question.
Yes, so this is for 2 points, right?
For 2 points, yes.
2 points, right. So the other points are...
This, you can take any 2 points, and if the line joining them is either horizontal or vertical, we can join it. But this line is not, so we could not join it here.
I see. So there are actually 4 points, right?
Yes, there are 4 points.
That's, I guess the order matters, right? So the order in which you do them matters.
No. You can pick any 2 points. You can pick all of these pairs, but the only pair that was horizontal, led to a horizontal line, was this pair.
Horizontal, it has to be horizontal.
Yeah.
The fact that this is very sensitive to the coordinates, like
Yes.
the system, is a problem? Like,
No, think to the way to, that's a very good question. The question was about what if you have points in general position, none of them are axis aligned. So the evolution stops immediately. These are motivated by partial differential equations. They model solutions to stable solutions to the differential equations, and therefore they are designed to be nice. Yes.
You said that if there are several pairs of points which are horizontal,
Yes.
does the order matter?
No, you can add all of them.
Then the order, you
Yeah.
can show that the order doesn't.
Yeah, you look at all points in your existing set and join the horizontal over. Yeah,
all of them.
all of them.
I see.
In one. So this is a geometric action that is applied on old set to create the new set.
So,
Yes.
yeah, one question. So you said that this is a generalization of convex hull.
Yes,
Why
because
is
you can
that?
say that you will not put this precondition. Then it is convex hull.
Sure. But
If and only if true.
Oh, okay.
Yes. So the question is whether it stabilizes. This particular example stabilizes. What do you think? Does it stabilize in general? Actually, what we can prove is that in 2 dimension, it does. Everyone stabilizes. All this evolution will always stabilize. In 3 dimension, it doesn't. Okay. 3 dimension, there is the smallest example. By the way, this was already known in mathematics literature since the 70s, I think. We rediscovered it. So here is the entire translation table between, oh, sorry. Yeah.
Is there also a way to get these, but instead of drawing it from the points, the other way around? You start
From
for
outside.
convex hole, for example,
Yes.
you can take intersection of our
Yes.
spaces.
Yes.
Is there some similar thing
Yes,
here?
when we try to identify the infinite union of these sets, because these sets may not stabilize at a finite number of steps, you can define it from outside as well. However, the inner step translates into communication complexity. What I mean by that is that let's call these laminates. If a point appears for the first time in the second laminate, this means it will represent a computation that needs 2 bits of communication. So yes, that's a very good question. We can define things from inside as well as outside. Typically, when you define things from outside, you take a closure, which actually adds spurious solutions, as we'll show. We do not need to do that. Yes?
So I'm not sure, you said in 3 dimensions it doesn't stabilize, but the separation only adds points, never deletes points, right? So
Yes.
shouldn't in the limit everything stabilize, even in 3 dimensions?
So think of it in this way. It's like you always move halfway to the destination at every iteration.
Yeah, so in
so
the
you
limit you will get there.
But the limit is not reachable. That does not have a perfectly secure protocol.
I see.
So typically mathematics literature have been taking the closure of these sets and investigating it. We have identified a very new algebraically well-behaved set of things, set of convex sets that can characterize these sets, and they need not be closed.
I see, you're saying for any finite number of steps, it doesn't terminate. That's basically the
Yes,
statement.
yes. So here is the translation table. If you give me a task and ask me, does this have a B-bit protocol? I translate it into an initial set of points and a query point. If I want to answer this question, is there a B-bit protocol for this task? I compute the bth laminate and test whether this query point belongs to the bth laminate or not. This connection is if and only if. So if there is no B-bit protocol, this query point will be outside the bth laminate. If yes, we can retrace how that point was added during recursion, and that translates into the optimal protocol. If there is no such B protocol, then it is outside the set. And we can also ask these questions for the hull where you are not given this bound. We can ask, is there a secure protocol for a task? And we can ask whether the query point lies in the hull, not in a specific laminate. Okay? Any questions, any doubts at this? Yes?
So I assume that the right answer is decidable, right? I mean,
Yeah, we have to prove this.
right.
These are unknown.
Okay. And the complexity of
Oh, this is a very good question. In this part of the research, like it is doubly exponential. Quantifier elimination is free for us. When we deal with this, we did not do a good job of estimating it. It's a tower of height 5. Okay, just like cake cutting algorithms, by the way. Okay.
Sorry.
Yes.
One basic question. What does a B-bit protocol mean?
100-bit protocol, so that a protocol has 100 bits of communication.
Okay.
Okay. So these things also show up on. Yes.
So if you have, say, irrational probabilities,
So
communicating bits is the right model. Maybe you have other alternative communication models.
So this is a good question. We are working in the Blum-Schultz-Smale model. Irrational numbers are there, like random bits.
But you cannot communicate an irrational number, right?
With certain probability, I can send you a bit which is irrational, and that subsumes this part.
The probability can be irrational, but you cannot communicate an irrational number.
Yes, I can send you a one whose expected value will be. Yeah.
But the output is bits, right? At the end of the day, the output
No.
is discrete.
No, it's discrete, but need not be bit.
Okay.
So yeah, the problem for bit output is well known, resolved. So the non-triviality starts at output 5. Okay. Okay. So these lamination hulls can model problems from optimization called a relative convex hull. So all applications in computer science materialize through this connection. And lamination hull in general is defined by a parameter set lambda. And the precondition says that you can join 2 points PQ by a line segment if P minus Q belongs to this parameter set lambda. Okay? So in particular, if you take the 2 axes as your parameter set, then this coincides with what I explained previously. Okay? So this is just a special case of this. Any questions, any doubts? Should we move ahead now? Okay. So let me motivate this problem again. We have Alice and Bob with private inputs, and they are going to communicate with each other. Kushilevitz already gave us this characterization for deterministic function. So what I'm going to do in the next few slides is reimagine that using our presentation, okay? Because that was one of the first steps, is a new interpretation that helps us go to randomize, but it should already subsume the deterministic case. So here is the main technical challenge. If Killian's obstruction is there, that is embedded OR, then the function obviously does not have a secure protocol. But if Killian's obstruction is not present, then it may or may not have a secure protocol. So we did not know how to solve this part for randomized case. So let me start with a simple example of the auction functionality. We assume Alice has odd bids, Bob has even bids, and the winning bid is the output. We just need to remember the colors of the output. We do not need to remember the function itself. So Kushilevitz protocol says that given the output, whether it is 4 or not, we already know whether the Bob's bid was 4 or not. So Bob can reveal this information. So Bob announces whether his bid is 4 or not. Condition on this output being input being not 4, Alice can then reveal whether her input was the lower row or the upper row. This is a secure protocol for auctions. This is basically where the auction ticks down, and you raise your hand whenever you want to bid for it. And if there are collisions, then it is resolved arbitrarily in a specific order. Okay, so let me show you how we reimagine this protocol in our new framework. So one change, so to begin, what we did was we assumed that Alice and Bob have uniformly random and independent inputs. So as the protocol is evolving, suppose the partial transcript is tau. Alice is about to speak next, and based on her bit, either the protocol evolution goes left or goes right. But Markov tells us that Alice's message can only reveal information about her input. She cannot reveal additional information about Bob's input. So the way to think about this is that at this point of the transcript, we could have talked about what is the conditional distribution of Bob's inputs. Given the partial transcript, what is the probability distribution of Bob's inputs? And on the left and right subtree, they will remain the same. Okay? So this is a condition that is enforced by Markov's constraint. And just based on that, we can build secure protocols. So we will call them siblings, and they can be put together or bonded. So let's begin at the end of the protocol. When the protocol terminates, we know that either the output is 3, 2, or 4. If the output is 3, we know that Alice's input must be the top row, and Bob's input must be the first left column. If output is 2, then we know Alice's input must be the lower row, and Bob's input must be the left column. And if the output is 4, we know for sure that Bob's input is the right column, but Alice's input are equally likely. Okay? It's not that it is 1/3, 2/3 probability. It has to be half-half to be secure. Okay? So given these 3 things, now let's try finding siblings. Note that these 2 are siblings, because Bob marginal distributions are same. So we can join them into a new partial protocol. And now look, these two are siblings because Alice marginal distribution is the same. We can combine them to get the algebra, okay? So now it gives a feel why lamination hull needs to ensure that certain projections are equal, and only conditioned on those preconditions, we can convex combine them. This idea generalizes, and it basically reduces to some, like our approach, looks similar to this. We start with the initial set, we compute the bth laminate, and test whether the query point, the function, end function that you are targeting, lies in the bth laminate or not. Okay, any questions, any doubts? I'll quickly go over the last part.
And
Yes.
is uniform distribution
Yeah.
kind of universal, or sometimes you have to look at different distributions?
So for perfect security, this does not matter. However, you can change this. So the topology of the shape does not matter on this. We can prove that. But specifically, to answer your question, the shortest answer is, for perfect security, you can choose arbitrary distribution. We chose uniform. That's a very good question, actually. Any questions, any doubts? So then I will, so we have seen such a connection previously in distributed computing, where there was a connection between deciding whether certain tasks can be performed in a distributed computing setting or not. And this work established a connection to topology, where they identified topological obstructions to distributed computing tasks. In our case, the connection is much deeper. We not only show obstructions, we actually can find the optimal protocol if it exists. And most excitingly, we get to build our own math. In their case, the math was already there in topology. Okay? Any questions and doubts? Then we can move ahead. Okay, so here comes the most challenging part that we resolved in our recent Fox paper. So previously, we were given a bound B, and we had to test our query point in the bth laminate. Now, this evolution might not stop, and we have to compute the membership of the query point in the lamination hull, which this problem might be undecidable. Why? Think about halting problem. If I ask you whether a Turing machine stops on an input X in 100 steps, that is very easy to answer. However, if I ask whether it stops at all, that becomes undecidable. So this has a similar flavor, and it possibly could have been the case that testing membership in the hull, not the laminates, could turn out to be undecidable. So we resolved this problem in a recent paper. The fascinating side effect here is that we can answer yes or no, whether there exists a protocol or not, in time that does not depend on the round complexity of the optimal protocol. It's independent of that. But to construct the optimal protocol, we'll need that much time. Okay? So think of it in this way. We have the ability now to compute the closure of all classical computation. Okay? So at how much time do I have? Or I will just wrap up. Okay, I will wrap up. So at a very high level, we have two pillars of our contribution. There is an entire geometric pillar, which basically shows that to understand the geometry of the lamination hull, you just need to understand it at a few represented appropriate points. And to understand it at appropriate points, we have to build a new type of algebra. This algebra solves, it looks like linear equations, but you do not work over numbers. You work over convex sets. So you talk about dilation of a convex set, Minkowski sums of those convex sets, and you want to find smallest simultaneous solution. So we had to build these two entire pillars to resolve this problem. Let me quickly go over this, lots of pretty pictures. So just to conclude, so again, let me thank all the organizers. And if you want to hear more about the underlying math, I will be giving a lecture on the underlying math sometime soon. And several funding agencies helped me concentrate on this problem for quite a long while. Any questions? Okay.
Any questions?
Yes.
So for the case of deterministic functions, we already had the solutions, right?
Yes.
So if you look at this through your framework, so
Yes.
does it correspond to some degenerate form of these things?
Yes,
Or,
that's a very good question. It basically says that every leaf can be combined into the tree once. There's only one way to do it.
and that makes
And
the
that's
whole
the,
thing, very simple.
whenever you cut, outputs always separate and you have the problem size goes down every step. That's the solution. And there is a worked out example on a slide on my webpage. I can point it to that. So there, you must use the base cases in 2 different ways to get a solution. So it is qualitatively quite different. But let me tell you one thing that's possible to connect to something that Rafi had mentioned, that you tend to a point, but you might not reach there. So they might admit statistically secure protocols. However, the rate at which you approach that matters, and that could be a future direction of study. So you can talk about marginal utility of communication as well. Yes?
Are there other, besides deterministic protocols, are there other like special classes of randomized protocols that are somehow simpler?
Yes, up till 4 output. We have a list of all the things that could happen, and we can show that the depth of the protocol is at most 2 or 3 or 4, right, Manoj? You have also a paper on this, right? Like 2-3 round protocols. Yeah, so it can go a little bit more, but 5 the magic starts, and it can keep going on and on and on and on and on. So there are. So let me put it this way: we have a result that says that you give me a bound, 100 bounds. I can give you a 5 output function that needs 100 bits of communication. You give me a new bound 1 million, I will give you a function that of 5 outputs that will need 1 million bits of communication.
These protocols that don't converge, do they depend on having like irrational probabilities?
No,
Even rational?
irrationals are free for us. That's not the point. It's truly a limitation of communication. It's Markov limiting us.
We had such protocols even in the deterministic case. What's new here is that you're basically pushing the big tables to the precision of the numbers,
Yeah.
right?
Yes. So that's very correct. What we can, I think, prove that if you invest 100 bits, you can get something exponential in 100 close to ideal behavior. If you spend 200 bits, you will get exponential in 200 close. Yes.
Let's thank Maji again.
Yeah, just 2 hours. Just a couple of quick additional announcements. So what do you get? You have 2 hours for lunch. Come back at 1:45 for the next talk.